Welcome! In this session, we're tackling LeetCode problem number 342, power of 4. This problem challenges us to determine whether a given number is a power of 4. It's a great opportunity to explore bit manipulation and mathematical properties. Let's dive right in. In this problem, we are asked to determine if a given integer, n, is a power of 4. If it is, we return true, otherwise, we return false. A number is considered a power of 4 if there exists some integer x such that n equals 4 raised to the power of x. For the input, we receive an integer n, and the output is a Boolean value, true if the condition holds, or false if it does not. To better understand the problem, let's consider a few examples, starting with n equal to 16. Here, for the input n equals 16, the output is true. This is because 16 is indeed a power of 4, specifically, 4 raised to the power of 2 equals 16. Now, in another example, if we take n equals 5, the output would be false. This is because 5 cannot be expressed as 4 raised to any integer power. So, while 16 satisfies the condition, 5 does not. Let's look at one more example to further solidify this concept. Consider the input n equals 1. In this case, the output is true because 1 is a power of 4. In fact, it corresponds to 4 raised to the power of 0, as any non-zero number raised to the power of 0 equals 1. Moving beyond these examples, let's take a look at some constraints and edge cases that will help us better understand the problem context and the kinds of inputs to expect. First, for negative numbers like n equals -16, the output will always be false because raising 4 to any integer power will always result in a positive value. Next, the case of n equals 0 is also straightforward. 0 is not a power of 4, as no integer exponent can satisfy the equation 4x equals 0. On the other hand, n equals 1 is a valid power of 4, as we discussed earlier. For non-powers of 4, such as 5 or 6, these numbers will always return false. Lastly, the problem requires handling very large powers of 4, such as 4 raised to the power of 10, which equals 1,048,576. Ensuring that our solution is efficient within the given constraints is crucial for these large inputs. To determine if a number is a power of 4, we need to verify whether it can be expressed as 4 raised to some integer exponent. There are multiple approaches to tackle this problem, starting with the brute force method. This approach uses iterative division to check if the number repeatedly divides by 4 without leaving any remainder, eventually reducing to 1. The steps are straightforward. First, confirm that the number is positive, as powers of 4 are always greater than 0. Then, while the number is greater than 1, check if it's divisible by 4. If at any point it's not, we can immediately return false. Otherwise, keep dividing by 4 until the number reduces to 1, which confirms that it is indeed a power of 4. While this method is simple, it involves multiple division operations, which makes it less efficient when dealing with very large numbers. The time complexity here is logarithmic, as the number of divisions depends on the size of the input, but the space complexity remains constant since no additional memory is used. Now, let's look at a more optimized mathematical approach. The key insight here is that powers of 4 are a special subset of powers of 2. Specifically, for a number to be a power of 4, it must first be a power of 2, and the exponent of 2 must be even. For example, 4 is 2 squared, 16 is 2 to the 4th power, and so on. Using this observation, we can define 3 conditions that must all be satisfied. First, the number must be greater than 0. Second, the number must be a power of 2, which we can check using the bitwise operation n and n1 equals 0. This ensures that only one bit is set in the number's binary representation. Finally, the number -1 must be divisible by 3, as all powers of 4 leave a remainder of 1 when divided by 3. By verifying these conditions, we can determine in constant time whether a number is a power of 4. This approach is both elegant and efficient, with no notable drawbacks. Another efficient solution involves bit manipulation. Here, we focus on the binary representation of powers of 4. A unique property of these numbers is that their binary form always has a single 1 bit located in an odd position, such as 1, 100, or 10,000. To leverage this, we use a bit mask to verify the pattern. Specifically, we first ensure that the number is a power of 2 by confirming that n and n1 equals 0. Then, we use the bit mask 0x55555555, which in binary alternates between zeros and ones, ensuring that the 1 bit is in an odd position. If the number passes both these checks, it is confirmed to be a power of 4. This method is highly efficient, operating in constant time and space. However, it does require familiarity with concepts like bit manipulation and bit masks, which might make it less intuitive for some. After evaluating these approaches, the optimized mathematical method emerges as the most suitable solution for this problem. It is efficient, simple to implement, and leverages the mathematical properties of powers of 4 in a clear and concise manner. While the bit manipulation approach is equally efficient, its reliance on bit masks may make it less accessible to those unfamiliar with low-level operations. On the other hand, the brute force method, though easy to understand, is less optimal due to the repeated division operations, which can become computationally expensive for large inputs. Each approach has its trade-offs. The brute force method prioritizes simplicity at the cost of efficiency, while the mathematical approach strikes a balance between clarity, speed, and robustness. Ultimately, the mathematical approach provides the best combination of these qualities, making it the preferred solution for this problem. To determine whether a number is a power of 4, we follow a structured approach. First, we validate the input to ensure it's a positive integer since powers of 4 are always positive. If the input number is less than or equal to 0, we can immediately return false. Next, we employ an iterative division method. Starting with the input number, we repeatedly divide it by 4 as long as it remains divisible. This process systematically removes factors of 4 from the number. For instance, if the input is 64, we divide it step by step. 64 becomes 16, then 4, and finally 1. This confirms that 64 is indeed a power of 4. On the other hand, if the input were a number like 20, the division process would terminate early, indicating that it is not a power of 4. After the iterative division completes, we perform a final check. If the resulting number equals 1, we return true, confirming that the input was a power of 4. Otherwise, we return false. Let's consider a few edge cases. For example, the number 1 is a valid input because 4 raised to the power of 0 equals 1. Numbers that are not divisible by 4, such as 5, 10, or 18, will fail the divisibility check and return false immediately. For larger numbers, this approach remains efficient because the size of the number is reduced significantly with each division, ensuring the algorithm handles even very large inputs without performance issues. The algorithm leverages a fundamental property of powers of 4. They can be divided by 4 repeatedly until the result is 1. This guarantees that only numbers of the form 4 raised to some non-negative integer pass the check. The iterative division method is particularly efficient because the size of the input number decreases logarithmically with each step. For instance, if the input is 1024, the algorithm performs only 5 divisions, corresponding to the base 4 logarithm of 1024. It's worth noting that while all powers of 4 are also powers of 2, the reverse is not true. Numbers like 2, 8, or 32 are powers of 2 but fail the stricter condition of being divisible by 4 repeatedly. Additionally, this algorithm is highly space efficient as it doesn't require any additional data structures. It operates directly on the input number, using only basic arithmetic, which keeps the space complexity constant. We can further enhance the algorithm with a few optimizations. For instance, if the input number is not divisible by 4 during the first check, we can terminate the process immediately, avoiding unnecessary computations. Additionally, we can replace the iterative division with a mathematical approach using logarithms. By calculating the base 4 logarithm of the number, we could check if the result is an integer. While this eliminates the need for repeated division, it introduces floating point operations, which can sometimes lead to precision issues in certain programming languages. Finally, in terms of complexity, the iterative division approach achieves a time complexity of O log base 4 of n, as the number's size is reduced by a factor of 4 at each step. The space complexity remains O(1), as no extra memory is allocated beyond a few variables. This makes the algorithm both fast and memory efficient for a wide range of inputs. This Python code solves the LeetCode problem number 342, power of 4. The goal is to determine if a given integer n is a power of 4. Here's how the solution works. 1. Initial check. The function first verifies if n is a positive number. Powers of 4 are always positive, so if n is less than or equal to 0, we can immediately return false. 2. Power of 2 validation. Powers of 4 are a subset of powers of 2. For a number to be a power of 2, it must have exactly one bit set in its binary representation. This property can be validated using the bitwise expression n and n1 equals 0. If this condition fails, the function returns false. 3. Odd bit position check. Powers of 4 have their single set bit in an odd position, e.g., 1, 4, 16, etc. To confirm this, the code uses a bit mask 0x55555555, binary 101010 which has bits set only at odd positions. The expression n and 0x55555555 equals 0 ensures that the set bit of n aligns with an odd position, confirming that n is indeed a power of 4. This solution is efficient, with a constant time complexity of 1, as it relies solely on bitwise operations and basic checks. This is the Java implementation of the power of 4 problem, using the same logic as the provided Python solution. The method checks if the number is positive, verifies that it is a power of 2 by ensuring only one bit is set, and finally confirms that this bit is in an odd position using a bit mask 0x55555555. Key differences include the use of Java's primitive data types and the class structure specific to Java. To determine if 16 is a power of 4, we start by checking if the number is positive. Since 16 is greater than 0, the first condition is satisfied, and we move forward. Next, we verify if 16 is a power of 2. This involves checking whether there is only one bit set in the binary representation. The binary form of 16 is 0b10,000. Using the condition n and n1, we compute 16 and 15, which simplifies to 0b10,000 and 0b01111, resulting in 0. This confirms that 16 is indeed a power of 2. Now, we need to ensure that the single set bit is in an odd position. For this, we use the mask 0x55555555, which highlights odd bit positions. Applying the condition n and 0x55555555 equals 0, we calculate 16 and 0x55555555, or 0b10,000 and 0b10,000 which results in 0b10,000. This confirms that the set bit is in an odd position. Since all conditions are satisfied, we conclude that 16 is a power of 4 and return true. Now, let's analyze the case of n equals 8 to determine if it's a power of 4. First, we check if the number is positive. Since 8 is greater than 0, this condition is met. Moving on, we test if 8 is a power of 2. The binary representation of 8 is 0b1000. Using the condition n and n1, we compute 8 and 7, which simplifies to 0b1000 and 0b0111, resulting in 0. This confirms that 8 is a power of 2. Lastly, we verify if the single set bit is in an odd position using the mask 0x55555555. The condition n and 0x55555555 equals 0 checks alignment with odd positions. Performing 8 and 0x55555555, or 0b1000 and 0b101010101010101010101010101010 results in 0. This indicates that the set bit is not in an odd position. Therefore, while 8 is a power of 2, it fails the odd position test, and we return false. Let's examine n equals 5, which is neither a power of 2 nor a power of 4. First, we check if the number is positive. Since 5 is greater than 0, the first condition is satisfied. Next, we check if 5 is a power of 2. The binary representation of 5 is 0b101. Using the condition n and n1, we compute 5 and 4, which simplifies to 0b101 and 0b100, resulting in 0b100. Since the result is not 0, this indicates that 5 is not a power of 2. Because 5 fails this condition, we don't need to check further, and we return false immediately. To summarize, the solution involves three key steps. First, we verify that the number is positive to ensure it's a valid input. Next, we check if the number is a power of 2 by confirming that it has exactly one bit set in its binary representation. Finally, we ensure that the single set bit is in an odd position using the mask 0x55555555. This sequence of checks guarantees that only numbers that meet all three criteria qualify as powers of 4. For example, powers of 4 such as 1, 4, and 16 pass all tests, as their single set bit is in an odd position. On the other hand, powers of 2 that are not powers of 4, like 2, 8, or 32, fail the odd position test. Non-powers of 2, such as 5, fail the earlier conditions outright. This systematic approach ensures accuracy in identifying powers of 4. The time complexity of this solution is O(1), meaning it operates in constant time. This is because the algorithm involves a predefined number of operations, such as bitwise operations and comparisons, all of which execute in constant time regardless of the input size. First, we check if the input n is less than or equal to 0. This is a single comparison operation, which takes constant time. Next, we determine if n is a power of 2 by evaluating the condition n and n1 equals 0. The bitwise n operation here is efficient, as it directly manipulates the binary representation of the number. This step also includes a simple comparison, which is constant time as well. Finally, we verify if the single set bit is in an odd position by performing n in 0x55555555 equals 0. This involves another bitwise n operation and a comparison, both of which are performed in constant time. Since each of these steps is independent of the size of the input and executes in O(1), the overall time complexity of the algorithm is O(1). The space complexity of this solution is O(1), meaning it uses a constant amount of memory regardless of the input size. First, the input n is passed to the function, which occupies a fixed amount of space. The intermediate calculations, such as n and n1, and n in 0x55555555, involve bitwise operations performed directly on the input integer without requiring additional memory allocation. These calculations are done in place, leveraging the existing storage for n. Lastly, the return value, which is either true or false, is a boolean that also occupies constant space. Since no additional data structures or variable allocations are introduced, the algorithm consistently operates within a fixed memory footprint, ensuring that the space complexity remains O(1). A naive approach to check if a number is a power of 4 would involve repeatedly dividing the number by 4 until it either becomes 1 or is no longer divisible by 4. While this method is straightforward, its time complexity is O(log_4 n), because the number of division operations required is proportional to the logarithm of n with base 4. However, it still maintains a space complexity of O(1), as no extra memory is used. In contrast, the optimized solution we're discussing makes use of bitwise operations to directly determine whether the number is a power of 4. This significantly reduces the time complexity to O(1), as the operations are performed in constant time, irrespective of the input size. The mathematical reasoning behind this efficiency lies in the nature of bitwise operations. They operate on fixed-size integers, such as 32-bit or 64-bit representations, and their execution time does not scale with the value of n. Since the algorithm involves only 3 such constant time steps, the overall time complexity remains O(1), making it far more efficient than the naive approach for larger inputs. In terms of best, average, and worst-case analysis, this algorithm consistently performs with a time complexity of O(1). The reason for this uniform performance is that the algorithm always executes the same fixed sequence of operations, regardless of the value of the input n. Whether n is very large, very small, or any value in between, the same constant time steps are performed, ensuring predictable and efficient execution. The algorithm's space complexity also remains O(1) in all cases, as no additional memory is allocated. To summarize, the optimized solution is both time and space efficient, operating in constant time and space. It outperforms the naive approach, which has a time complexity of O(log_4 n), by directly leveraging bitwise operations and mathematical properties of powers of 4. These optimizations enable the algorithm to deliver consistent, high-performance results regardless of input size. When solving the power of 4 problem, There are several common pitfalls to watch out for. First, it's crucial to ensure your solution handles only positive numbers. Since powers of 4 are always greater than 0, including a check like n greater than 0 can immediately rule out invalid inputs. Next, be cautious with logarithmic calculations. While using log4 n might seem straightforward, floating point arithmetic can introduce precision errors, leading to incorrect results. For example, log4, 16, might not yield exactly 2. Instead, consider integer-based approaches that avoid these issues. Another mistake arises with bit manipulation. While a number with one bit set might seem like a power of 4, this is only true if that bit is in an even position when using zero-based indexing. This subtlety often gets overlooked. Additionally, iterative approaches, such as looping through powers of 4, can work but become inefficient for larger inputs. Finally, edge cases like n equals 1, n equals 0, and large numbers should always be tested to ensure your solution is robust and handles all scenarios correctly. Understanding the unique patterns and properties of powers of 4 is key to solving this problem efficiently. In binary, these numbers display a clear structure. They have exactly one bit set, and that bit always appears in an even position, such as 1, 100, or 10,000. Mathematically, a number is a power of 4 if it's a power of 2 and divisible by 4. You can verify the power of 2 condition using n and n1, and confirm divisibility by checking if n%3 equals 1. Interviewers often favor bit manipulation for its efficiency, so be prepared to explain how binary representation supports your approach. For time complexity, aim for constant time solutions, such as using bitwise operations or mathematical checks. While iterative or logarithmic methods are valid, they may not meet optimal performance expectations. Additionally, this problem connects to several related patterns you might encounter in interviews, such as power of 2, power of 3, ugly number, and happy number. Studying these problems can deepen your understanding of similar concepts and techniques. There are multiple approaches to solving the power of 4 problem, each with its pros and cons. A mathematical approach might involve using log4 n to check if the result is an integer, though this can run into precision issues with floating point arithmetic. Alternatively, bit manipulation offers an efficient solution. By ensuring the number is a power of 2 and that its single set bit aligns with an even position using n and 0xaaaaaaa equals 0, you can confirm it's a power of 4. However, this requires familiarity with binary representation. For those who prefer simplicity, iterative division works by repeatedly dividing n by 4 until it equals 1. While intuitive, this method has a slower time complexity of O log n. Finally, pre-computing all valid powers of 4 up to a certain limit allows for O1 lookups, though it comes at the cost of additional memory usage. Each of these methods has trade-offs, so understanding the context of your problem is essential when choosing the right approach. Great job! To recap, we solved the power of 4 problem by leveraging mathematical insights and bit manipulation. Remember to practice similar problems to strengthen your problem-solving skills. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!